Yes, sir.
Okay, we have been discussing about second hormone generation. I gave you the basic ideas. We said we start with neodymium reactor. This has 5 nanoseconds, let us say 100 millijoule, 1 milliradians, 1064. That's all you need to know. When I put all this, you know the complete picture about neodymium. Then, in the last lecture I told you, if you want to produce second hormone generation, you should know the right type of material which will produce second hormone generation. Phase matching condition should be satisfied. There, the material should be carefully chosen. One such material is like this. This is called KDP, potassium dihydrogen phosphate. This is the optic axis, P, then actually this is exactly what, this is the way it is all done. I cut it like this, I cut it like this, so then if I send the laser beam like this, such that this angle is about 57 degree approximately. This is the phase matching angle for hormone generation. You will get omega 1 and then 2 omega 1, which is omega 2. Which means what comes out here will be, come back to this one.
Double frequency.
When you shine a light like here, you will lose at least usually 10% of the light by reflection. Then assume the crystal is perfect, which is not true. Always there is some loss, scattering. I lose usually 10%. Then here again I lose 10%. All put together 1, 2, 3, 30% is out. What is being done is only 70% of the photons are being converted into this one. But that is under ideal condition. Usually this is about 50%. The conversion efficiency is 50%. Now, what comes out usually, let us say I start with 100 millijoule. What comes out will be omega 1, which will be 1064. This energy will be about 20 millijoule. Omega 2 will be twice the frequency or half the wavelength. That will be 532 nanometer. This will be about 40 millijoule. Plus 20, 60, then you have 40 millijoule which have disappeared mostly as a heat. If I do very, very carefully, I can go up to 50. This is the usual and realistic condition. So what comes out is 10 millijoule. Then the question is, what is the pulse width? Is it decreasing or increasing? It was found out, since you have done the phase match condition, this does not affect the pulse width. It is not pulling it or sharpening it. So this will be 5 nanoseconds. Same way, the divergence also will be 1 milliradian. Not only that, the polarization also is the same. Polarization of fundamental is the same as the polarization of second hormone. Now, all these will be strictly true, but this is not strictly true, not always. There will be some kind of mispolarization, depolarization is always there. But this is not very important factor. other things are very important. Next step. Suppose I want to use another laser, I must buy another KDP crystal, only phase matching condition will be satisfied. This is what I told. Let us go there. There is a list of, this is what I will read out, or I will give you the, it's a long list, yes, but you should know at least few of them. Later you can read this book. Look at this one. Another crystal, ADP crystal. This is potassium dihydrogen phosphate. This is ammonium dihydrogen phosphate. This is best. I shall come to this one. 220 to 2000 nanometer. The threshold is 0.5 GW by centimeter square, and this is one. Another very famous is KDP. This is more or less. Only thing is this one. Now, damage threshold is 8.4, 8.5. Now look at this one. Lithium iodide. Lithium iodide. I am writing only few of them. This is best for 400 to 5000 nm. And this is lithium niobate 0.05. Next you see this tellurium crystal, or in fact you can put cadmium, germanium, arsenic. It's some crazy crystal. This is from 1 to 20 micrometer. This is 0.004. There is a reason why I take up only this. Look at this one. What is this one? Threshold. This represents the damage threshold. Look at it. I am going to focus the laser beam on this. This will produce a very high power density at this point. This should not damage. It should accept all the light and transmit it. This is called a damage threshold. Now between the two, look at this one. ADP and KDP are more or less same in the wavelength region. But this is how many times? 16 times better threshold. That means if at all I want to use a high power laser for hormone generation, I prefer KDP better than ADP. First point. Second point. What is this region? Transparent region. We have put from 220 to 2000 nanometer. What does it mean? That means, look at this one. Imagine I put 1064. It is producing 532. Both wavelengths should be allowed to go. Suppose this material absorbs. What is the use? I give money to the bank to send it to my people in India. If the bank takes the money, why should I will kick the bank people, right? They are supposed to take the this and give it there. They are not supposed to use it. This is what you can. The two material has a range of wavelength over which it will not absorb. This is called transparency. It will emit, it will allow
KDB transport all the
wavelength. 220 is ultraviolet. 2000 is infrared. That means these two are the best. Out of it, this is the best. That is why wherever you go, you will get KDP crystal, not ADP. Next point. So, these two crystals are, forget even ADP. KDP is a very good crystal for conversion of visible into ultraviolet. See, look at this is infrared, I have converted to green. Instead of this one, suppose I send 694.3. What is this laser? This is the first laser, ruby laser. Half the wavelength will be 7.2, okay? Nanometer. This is in the ultraviolet. So, I can buy a 2 KDP crystal, one for YAG laser, another for ruby laser. Next. Suppose I want to use a carbon dioxide laser for harmonic generation. I must use this. Because at this wavelength, these two will absorb. They will not allow, they eat all this one. But look at this. For carbon dioxide laser, what is the wavelength? 10.6 micron. So this is the best for carbon dioxide laser. Okay. So far, we don't talk about any semiconductor laser. We don't talk about harmonic generation from excimer laser. We don't talk about harmonic generation from nitrogen laser. Why? I told you, you must find the answer.
We are searching.
Find out, okay.
But
Right.
some of papers talked about, I think, exam laser with copper vapor. It's different.
Copper vapor is different story. After 2 or 3 lectures, you raise the same question. I shall explain what is this one.
Sure.
Okay, now come back to this one.
Professor, now the first one and the second one. Yes, can they use to Nadium Yak or Robi?
Yes,
Because this the wavelength and this.
I can use this or this. Okay? Both are really good. This is 10 times cheaper, easy money. But this has a low threshold, this is 16 times greater threshold. What is it? Gigawatt per centimeter square. If you focus it, you can find out what is the power per centimeter square. So this will withstand only this one. If it goes beyond this, KDP will get, ADP will crack, it will make a pit.
If it is more than 0.5.
Yes. For that, KDP is the best.
For the two lasers.
Yeah. For both laser, you can, KDP is the best. Because of this, anywhere in the research laboratory, people will have only KDP, not ADP. I am talking about YAG laser and ruby laser. I can go, next step I can go. As I told you, all so many lasers, I have said ruby laser, YAG laser. Occasionally CO2 laser. I am not talking about excimer laser, nitrogen laser, helium. There are hundreds of lasers. They are not used for harmonic generation. Why? You must find out. Next step. We will go to the next interesting step. All this time, in the last lecture, I said, look at it. PTW by PW will be some constant, something. Then this is the power from second harmonic, this is the power from fundamental. So this gives you conversion efficiency. Which means if I use 100 millijoule, I will get 50 millijoule in second harmonic. right? That's the meaning of this one, under the best condition. Now, let us look at this one. In a YAG laser, when you say this is the 100 millijoule is coming out, what is the power existing inside? What is the energy existing inside?
More than 100 millijoule.
Why?
Because
Because, yeah, yes.
the amplification of the light inside the reservoir.
Because the flash lamp has got a high voltage and the capacitors, we can get more energy than the output.
No. The flash lamp is producing only population inverse.
Yes.
Okay. But here I am talking about 100 millijoule of YAG laser output. Inside we have more, you will have 200 millijoule of YAG laser power inside.
Yes, more.
Why? That's my question.
Because the transmission of the mirror is 10%.
Correct. That is the answer. Look at it. One should be 100% mirror. This should be, let us say, 90% mirror. That means only 10% of the power existing inside is coming out. That means what is inside is, look at it, 100 millijoule at 1064. That's the meaning of this one.
This is the efficiency of the NDI.
Huh?
This is the efficiency. We talk about the efficiency of the NDI laser.
No. For any laser.
Well,
I will come back. You have any laser. Huh? I have one mirror. I have one mirror. We say the power that comes out from, you have this laser is 10 millijoule. Then what is the power existing inside? That will be 100 millijoule, or in fact 1000 millijoule, because the output mirror is reflecting by 95%. This is 100%. So only 5% is coming out. Now 5% is coming out means how much you will say? 100 by 5 into 10, this will be 200 millijoule power is existing inside. That's the meaning of this one. This is something like, imagine there is a war between two countries. If 100 soldiers are going from, let's say from India to fight with somebody, you must know, the other country know, there are 1,000 soldiers sitting there within India. They sent only 10% of them. Okay? Another 1,000, 2,000 are being produced, made ready to fight. Only 10% is coming out. That means you have more soldiers within the fort than coming out. Now the next question is this one. Instead of keeping the second harmonic crystal outside, why don't I put here? You understand the question? Jump. Because if I put my KDP crystal here, I can get, look at it, 1,000. I can get 500 millijoule. Because so much power will be inside. And all of them will produce second harmonic.
I think the reflection is, it will be in two sides like this. This mirror will reflect the light in the other side.
Yes. In spite of all this one, look at it. You have 100% mirror here. This is 90% mirror. Instead of keeping the crystal outside, I can put the crystal inside also. What is wrong? Why we don't do that? Or why, what is the advantage of keeping inside? Keeping the crystal inside is really good in this, because when we say 100 millijoule is coming out, 1000 millijoule is existing inside. If I put all the 1000 millijoule into the second harmonic generator, I would get 500 millijoule, or at least let me say 200 millijoule. So I will get almost 2 times a pump. So this is called intra-cavity harmonic generation. This is the advantage. But what is the disadvantage? What is the disadvantage? This looks very simple, but what are the advantage, disadvantage? Advantage I mentioned, the disadvantage is?
I think the KDB crystal has got one direction for the light to pass from it.
No?
From
Right.
inside?
Yes, inside it will allow the light to go back. No problem.
It will damage quickly.
That's the first thing. Since this is subject to a high power so many times, this is like a small, you take a small child and make it go back, you are torturing. This will get damaged very easily. That's one problem. Second problem.
We can't change it very easily.
Hmm?
If we want to put, we can't put it inside the laser easily.
No problem. No, it's easy. Next time you show me, I will show you.
Inside?
We can do. All this we will do, I will show you.
Okay.
The headache is, I tell you, when you put in, to get the laser action is very, very touchy. The alignment between this mirror and this mirror should be very careful, then only you will get a good laser.
Yes.
Now, when you put a crystal, it has its own refractive index. And the refractive index will keep on changing with the temperature. Where is the temperature?
From the
This
top.
will get heated. So, alignment is a big headache. You can get a good laser for a short time,
For a short time.
but after some time you will see it is giving more headache than an advantage. So, these people don't usually, no company will offer this one. You know who will use it? People like me who are
Experience.
professional, we know where to touch it. I want more power, so I will put it, I know how to handle it. It's like handling a snake. You know snake?
Yes.
The snake charmer knows where to touch it. Other people don't know. So this is touchy. But in principle it is allowed. It is good also. It is okay for the experts. Okay. That's all about it. Let us go to the next interesting thing. Next interesting thing is this. Look at this one. I start with argon ion laser. 10 watt. 10 watt CW. Allow the laser to fall on, look at it. This is the dye laser. Dye laser. Look at it. This is how it goes. The dye laser will be always like this. This is the active region for dye laser. Then you put one mirror, you put another mirror, I will get the laser out. This is an argon ion pumped CW dye laser. You studied about it?
It was the solution dilator.
What is it?
This is the solution?
Yeah, solution.
Okay.
Solution, the solution is flowing like a jet. Solution flowing like a jet. Note down, all note down in the side of the paper. I will show all of them. Laser, dye jet. you must spend at least 4 labs, 4 days with me.
Laser digit.
Laser digest. Put that, I will show you.
Digest.
All these I will show you in the lab. Okay. Next step I do something funny. So, yeah, I get the laser here. Now I put my crystal, second harmonic crystal. I get, for example, this is 488 nanometer. All these are realistic examples. I can get a laser at, let me say, 600 nanometer. I put this 600 nanometer, I will get 300 nanometer. You see the funny thing I have got? I started with the 418, now I have got 3 lasers. 488, this is the laser, I bought it. This is the what I can design it. 600. Now once we have designed, we did everything.
Yes.
And then nobody comes forward, that's a problem. I have to do everything, then I give it up, I got fed up. See, I can do something, then somebody should take over, then only I can go to another. If I leave it, it dies. That's a problem here. So this is 600 nanometer. From 600, I can get to 300 nanometer. Okay? Let's see the next step. Here, I put a prism. Then light goes, go here. Then what will I have it?
Tunable.
Yes, that's all. I can tune the laser. By rotating the prism, I can get the laser from 600 to, when I do this one, I can get the laser from 560 to 620 nanometer or 600 nanometer. That means over 40 nanometer I can rotate and get the laser. And then I have something funny here. I can get a laser from 280 to 300 nanometer. Look, first I tune it, get the laser at 560, and then I come here, adjust it, tune it, I will get the laser. So, I can get a tunable second harmonic generation starting from, look at this one, argon ion gas laser. It goes to liquid laser. It goes to solid state laser. You understand? I make 3 jumps. I start with the gas. Yes, sir. Check what? You can check before disturbing it. Okay. So you start with the gas laser, liquid laser, and then this becomes the solid state laser.
This is very good.
Very good. In fact, this person, this Demtoda, he's an expert. I love his lecture. I have attended his lecture many times.
This one?
Yeah. I like him very much. Personally, I have worked with him.
You studied with him?
Yeah. He's expert.
Doctor,
He is alive now?
Huh? No, he's dead. Look at this one. It's such a big book. And it's an expert book. I think it has gone to 3 or 4 edition. This is the biggest book for laser. He starts with the basics of laser, variety of laser, all harmonic generate so many things, and use them for spectroscopy, biology. It's a very big book. One person. It's in Germany.
Doctor,
Yes.
any way to do the second harmonic generation without we use crystal?
Without crystal second harmonic generation?
Any way to do this?
No. You can, instead of crystal, you can send it through some powder. You will get second harmonic, but very weak. This is what we said at the beginning. Without the crystal, you can get second harmonic, but the efficiency will be 0.001.
Random.
You will get very weak. You will see that one. That also will show you. Note down. second harmonic from powder. I will show you all these experiments. If you are ready to learn, I can show you 20 experiments which even in European country you will not see that.
We are ready. We are ready.
Yeah, you must come work in the lab.
We are ready.
You will see so many things can be done. Okay.
But you can give us time if you want from after 3 o'clock. If you want.
Let's see. First, let me finish the basics. Then I will take it. Okay. So 280 to 300 nanometer. Okay. This becomes something like a radio. I can tune here. I can get the laser from 280 to how much? 600. Look at it. 280 to 600 nanometer. How? Look at it. If I put a mirror, a light mirror with 20% reflectivity, I will get a tunable laser from 560 to 600. I send most of the light inside, I will get from 280 to 300. Already I have a laser at 488. So, it is like a variety of biscuit. You take a biscuit with chocolate, biscuit with cream, biscuit with salt. I have variety of chocolates, variety of biscuits, variety of lasers, yes.
The mirror will do the tunable from 200?
No, this mirror is to just reflect the light from here. The tuning can be done. Wait. This particular dye solution is capable of giving laser from 560 to 600 at a stretch.
Okay.
That's the nature of the dye solution. Now, which wavelength I want for laser determined by the prism. Good. Then, the prism and this mirror chooses the laser for me. Out of this, I take 20% for another experiment. I send 80% to produce harmonic generations, then I have this laser for another thing. All this because, look at it, I am a rich man with the 10 watt power. This is 10 watt power. What will come out here? Look at this one. At this point, this can be 30% conversion efficiency. That means this is 3 watt. Then 3 watt, 20% of 3 watt will be how much? It will be 60 milliwatt. And then I have so much here, 1 watt approximately. So I have a 1 watt tunable laser here, 60 milliwatt tunable laser. I have 488 10 watt. So I have variety of lasers now for variety of applications.
Any power you want to use for any material, you can put here.
Yes, I can do one experiment here, I can do another experiment here.
Or you can do with 3 watt, with the original.
It's up to you. It all depends upon this. Okay, next, let us go to the next step.
Doctor, can we use the output to bump another die?
You can. That's a good idea. You can do that one. For example, I can use this laser. Look at this one. I can use this, after all I have already 1 watt. I can use this laser to pump another dye laser. So, look at it. I can do this one. Put a lens. I put another dye jet. This is, look at 300, let us say. Then I put another grating. Look at it. The solution is flowing like this. Then I can get a, since I have 300, I can get a laser, look at this, from 400 to 500 nanometer. And then I can do harmonic generation from this also. So it is left to my imagination, money and expertise. So I can get a tunable laser from here to here, from here to here, from here to here. All are possible people have done, and this man has done everything. Damn it all. They were playing in the lab, something like that. Yeah. Okay. So much about second harmonic generation. Let us go to the third harmonic generation.
ما بكتب شو بكتب بالعربي شفت ليش؟ صحيح معي فلوس انا معي فلوس انا صحيح خليك مشوار جيب لي باك بكره امسك يا اخي جيب لي بكره والله ما اخذت بكره.
Let us do third harmonic generation. To do third harmonic generation, all that I need to do is this one. Here it is. First, draw this picture, then things will be clear for you. This is 0, 90. I imagine I have taken a crystal. This is optic axis. This is the angle. This is the angle I am talking about here. Then you remember we have this equation. We have this equation. Keep this in mind. 1 over NE, refractive index of E ray is cos square alpha over N1 square plus cos sine square alpha over N2 square. This is alpha put theta, that's all. So the refractive index for this one is a function of this. Okay? On the other hand, refractive index of O ray is not a function of theta. It is a constant. It's some value. Now then, I draw the refractive index. This is refractive index. This is 1.5. This is 1.8. Now this represents 1.6, 1.7. Now next step, this represents N O of omega. That represents flat line for refractive index of O ray or frequency omega. Then next step, this represents N out for 2 omega. While as the frequency increases, the refractive index increases and the speed of second harmonic is less. Then this should be something like N0, 3 omega. It will be a straight line only for O ray. For an E ray, it will depend on the theta. So what happens is, for E ray, this will be N E omega. For E also, for a higher frequency, refractive index increases. So it should be just parallel like this one. Yes. Remember at 0, at optic axis, O and E are the same value. Am I right?
And they go from optical.
Go together.
Same speed.
Here, O and E, omega will go together, but not 2. Understand? So, omega of O, omega of W go together. But O of 2 omega will not go with this. It will go slow. Understand? Yes, you must remember. Okay. That is shown already by this. Out of this, there is one point which is interesting. Look at this one. Which is what is this point? This point, I would say 1, or let me say 3. This is 2. At point 3, the third harmonic of E ray and first harmonic of O ray has the same refractive index. Understand? At this point, look at this one. This is the intersection between the refractive index of O ray of omega and E ray of third harmonic. That means both will have the same refractive index. That means if I send the laser beam, look at it. Suppose this angle is 72 degrees let me see. Then all the type degrees, look at the picture, then you will have it. Now look at it. This is 90 degree. This is 0 degree. Suppose I start from this one. I send the laser beam like this, 72 degrees. Then the third harmonic of E ray, first harmonic of O ray will go together, so I will have efficient conversion of fundamental into third harmonic. In the same way, if I launch it at this angle instead of 72, it may be 53. I don't know. I'm just giving an example. Take the same crystal. I send it. Look at this one. Ring chalkish now. If I send it like this, I will get second harmonic. 2.
So we just change the angle.
And come to that one. That means the same KDP
Can
I
produce.
can use it for second harmonic or third harmonic. This is in principle. In practice, there is a problem because this surface should be cut properly.
So we can't do
You
get
can
7.
do and get some light output, second and third harmonic, but the best way is to buy the same 1 kdp for second harmonic, another kdp for third harmonic. I can interchange. I will get some, but it will be very weak. Okay, under this condition, look at this one. I start with 100 millijoule, 5 nanosecond, 1 milliradian, 1064 nanometer. I get maximum 50 millijoule, same, only thing is 532 nanometer. This is second harmonic. In third harmonic, this will be still 10%. See, from here it is 50%, from here it is only 10%. I can get usually 10 millijoule at 355 nanometer. That is, you divide the wavelength by 3, multiply frequency 3 times, or divide the wavelength 3 times. Is it okay?
This is okay, and the energy we calculated.
You will get only 10 millijoule. Okay?
Doctor, if we use third harmonic generation, we must put the second harmonic generation before it.
Yes.
But the output will be the fundamental and second.
No, we'll come to this. We'll come to this.
Okay.
Okay. In principle, I can do this way. Experimentally, what I do, look at it. I start with 1064. I can put the second harmonic generator. Then I will get 532. And then 1064. I can put third harmonic. I can get 355. So look, I have 2 different crystals. But instead of this one, I can do one more. Look at it. I start with the 1064. I get second harmonic generator. Then I put a third harmonic generator. The advantage of this one is, look at this. When it comes here, I will have omega, let's say omega 1 and 2 omega 1. Because we said only 50% conversion. That means this is 100 millijoule. This will be 20, this will be 50. Am I right? This is what I told you.
Yes.
Then, if I put third harmonic generator, then what happens? See, these two combine together. Look at omega 1, 2 omega 1 to give omega 3. Understand? 2 this is equal to omega 1 is omega 2 becomes omega 3. Fundamental second harmonic produce third harmonic. As I told you, I can choose this straight away from 1064 to third harmonic, or I can go 1064 second harmonic and third harmonic. It was found that, look at it, this is equivalent to saying 3 photon interaction, right? 3 photon interaction. Because this is equivalent to saying, look at it, I produce omega 3, which is 1
Plus 1.
plus
Plus 1.
omega.
Yeah.
Whereas here what happened is, I get the same omega 3, this omega 2 plus omega 1, right? This is a 2-photon interaction.
Yes.
Always 2-photon interaction is stronger than 3-photon interaction. If you don't believe it, do this one. You are from Yemeni, right? This Friday, go to Baghdad. Till 7 o'clock, you want to meet one friend. You will meet him at that point, okay? 2-photon interaction. You ask 2 friends to come there at the same time, one of them will come late. Understand?
Yes.
Same way here. One of them will come late, one of them may not come at all. Understand? The probability of meeting 3 people together is far more difficult than making 2 people come together. I mean, whatever I said, I am telling you from an experimentalist point of view. All this can be shown theoretically. At the end of this one, I would request one Dr. Sandra, what is it? There is one theoretician.
Aslam.
What is it? No. Aslam?
Aslam Farouk.
He's not a theoretician. The other end there is one. Greek. I forgot. Wait. Alexander. No. All these.
واحد يوناني.
Andreas
What is
Andreas.
Andreas. Okay, I will catch him. He's a theoretician. He will give a same lecture, non-eruptics from theoretician point of view.
He gave me one course, master.
What course?
Analysis.
Analysis of what?
Information analysis.
يعرف.
تحليل البيانات. Analytical analysis. Mathematical analysis. اسمها تحليل بياني.
بيانات ايش؟
تحليل بيانات.
Information.
You attended?
I'm in Jordan.
Information
I like it.
analytical.
Thank God I never attended. If I attend, I will go crazy. I never understand. I'm not joking. All those theoretical things, it becomes a nightmare. I cannot sleep. It goes into my head, cracks. Anyway, that is my weakness.
Same for us.
For some people it is easy. Some people,
Some
they
people like
easily,
it theoretical. Some people.
they get very easy theoretical mind. Anyway, it's okay. So this is what is generally done. This is very efficient. In practice, what happens, I can tell you. What real happens is, if I start with the 1064 100 millijoule, I get 100 millijoule. I put the second harmonic generator. I usually get 30 millijoule. I don't get more than this. This is 10 millijoule, maybe 40 millijoule. Then I put them all together in the third harmonic. I usually get 10 to 15 millijoule. Look. Here is a fundamental, right? This is, I get another 10 millijoule in, I said, 532, 355, and then I will always get, look at it, 5 millijoule at 1064. You see, at this point I will get fundamental, second harmonic and third harmonic.
10 millijoule is useless.
Yes, useless. This is the realistic condition. Then what we do? Look. When it comes like this, what we do, look at this, the way I do. I put called beam block. Beam block means it will be a rough surface which will absorb all infrared radiation, because I don't want this 10 milliwatt infrared come out, because it will give a problem for me. I don't want it, I cannot use it, so it's a nuisance for me. Then I have 532, 355, right? Then look at it. I can put a dichroic mirror. Look at it, I put DCM. Tomorrow you are going to explain what it is. I put a dichroic mirror. I tilt it. Look at it, I just tilt it. Look at it. So both fall, and then this will reflect 355 and transmit 530. You see the funny point?
You will get one, 532.
No, watch out.
Two in another two direction.
I divert.
Separate.
Yeah.
All the trucks go here, all the cars go here. That's the way I do. Yes.
355, 3 is to 05.
Hello?
55.
نص 332 نص. لا نص لا 1000 1964
See, it's like a
1064
both come, I try, divert it. Now the question is, you must explain me how the direction is changed.
What is the name? DCM? Direct?
Put the word DCM, put the picture, then go to the net, you will find out.
Sometimes appear DCM another word.
That's what I say, go, find out. If you put this picture, put this DCM in your mind, you will never get, because there is no DCM can ever come here. This is a dichroic mirror. Only dichroic mirror can do this one. I would suggest you, why don't you give a talk sometime about dichroic? Similarly, you give a talk on different topic. I will give you.
I
Yeah.
can talk this one?
Yes.
We will do so.
Okay, so you give a talk on dichroic. Let us go to the next interesting topic. This is, we have seen all the important features of second harmonic and third harmonic. Can we do fourth harmonic?
What to do?
Can we do fourth harmonic?
Yes, we can.
Yes. All that I have to, now look at it. The best way I do, can I put a crystal here? I will not do that, because if I put fourth harmonic, what should I do? Look at it. Omega 1, 2 omega 1, right? 3 omega 1. So, I can use this, I can use this. If I use this, I will have a fifth harmonic, right? Instead, the best way, look at it. Go. I put second harmonic. Look at this one. Omega 2, omega 2. This become third harmonic generator. Sorry, fourth harmonic generator. So I will have omega 4, which will be 1064 over 4. This will be half of this one. 2, 6, 6. If this is 5 millijoule, this will be still very bad. 50 millijoule, this is 5 millijoule. Why? Why? Here you have, see, the conversion efficiency from 50 to 10 means 20%, right? Whereas this one, 50 to 5 means how much? 10%. 10%. So the fourth harmonic becomes far low. Why? Go back to the equation. In your equation you have, look at